The program chairs gave me a bit of a hard act to follow after this morning's keynotes. But today, my name is Michael. I'm here from LinkedIn, and we're going to talk about reducing mean time to resolution, known as MTTR, and false escalations, and how we do event correlation at LinkedIn. Event correlation, as Charity mentioned earlier, is difficult, especially the smaller you are. Getting the resources you need to do this becomes harder. LinkedIn is large, but what we've been able to build has actually required pretty little resources in all actuality, which is awesome. So what I'm hoping for you guys to get out of this is how you can take some of what we've done and build your own system. All right, so false escalations. I want everyone to put their hands up if you've been woken because your service is unhealthy because it depends on someone else and their service is broken. All right, like half the room. Keep your hands up if you've been woken because someone believes that your service is broken, but it's not. All right, more hands go up. And who has spent hours trying to work out why your service is broken only to find that it was a dependency that you couldn't really see? All right, for those people who didn't put their hand up, I want your job. Talk to me after. All right, so basically all of you in the room have experienced this. And so we too...
All right, we will go ahead and get this panel started in a minute or so.
We good? All right.
Michael, was that someone else's service?
Anyway, all right. So, we've all experienced this. It all is less than optimal, right? And you know, at LinkedIn, we have some of the same problems. So we tried to build this event correlation system to stop having these false escalations, but also to fix mean time to resolution. All right, so today I want to talk about the journey that we took in building our event correlation system. So I want to start by sort of talking about our problem statement and what the goals of our project were, and then guide everyone through architectural approaches, because as you'll find out, depending on your infrastructure, it's not a one-size-fits-all sort of deal. So talk about what the approaches are that you can take and how we built our correlation system around LinkedIn's particular challenges. And then we'll go and look at some takeaways, some results, and I'm sure there's going to be a lot of questions, so we'll leave some time for those. All right, so who am I? I'm Michael Keogh. I'm a staff site reliability engineer at LinkedIn. And I'm on a team called Production SRE. And Production SRE has 4 main goals, which I don't actually have up there. But most likely, well, they're on this slide, the 4 key tenets are basically reducing mean time to detect and mean time to remediate through building applications, provide direction on site monitoring, build tools for efficient site issue troubleshooting, issue detection and correlation, and assist in restoring stability during site critical issues. So yesterday I sort of talked about, in a different talk, about how my team restores stability. And today we're going to talk about you know, fixing mean time to resolution and troubleshooting and correlation. All right, so I want to visualize our problem statement from the perspective of an SRE. So firstly, as our services get more complex, our reliability can go down. As our services get more complex, the learning curve for engineers goes higher, especially in the microservices world. And then finally, as our services get more complex, the mean time to resolution can go up. And as you all know, higher mean time to resolution is bad for both our customers and also ourselves as engineers. So this project was about fixing false escalations, but also making a better experience for ourselves as engineers so we can sleep more, for our customers so they can use our site better. And what that comes down to is basically reducing mean time to resolution. So my boss gave me this problem statement and said, we want you to provide a unified API that can find the problem with a service in either real time or post hoc analysis after the event. And we want to be able to plug that into our automation systems. Then he said, we also want a web front end that allows engineers to sort of visualize the problem so they can do some introspection. And so we said, all right, let's do it. And to sort of scope the project a little bit more, basically the success criteria was to reduce MTTR on applicable incidents, and also to reduce false and needless escalations. At LinkedIn, we're lucky to, for some SRE teams, to have 12/7 coverage, so they've got a counterpart in the other half of the world to help them out while they sleep, but that doesn't apply to all teams. So we are trying to ensure that our SREs and our engineers as well can sleep as much as possible, and we don't escalate to a team who owns a front end whose service is hosed because there's some back end that's broken. It's not useful to anyone. So given this problem statement and our success criteria, we did have to sort of scope, what is in scope for this correlation system being able to detect and correlate. And so we said basically anything within the data center was in scope. So for example, internal metrics show that a front end or a middle tier has high latency or high error rates. We want to be able to work out what's causing that. We did say that if external monitoring sees something like slow, so we have third-party monitoring outside of our network, if they say we're slow, well, that's kind of out of scope because there's so many variables. There's the internet, there's DNS, there's CDN, etc. Really difficult for us to correlate against. And to be honest, we trust those systems, and we trust that we have the right monitoring in those events. So when it comes to the approach of building a system, an event correlation system, there's a few different approaches you can take. Real-time metric analytics, which is like basically streaming data at real time via something like Apache Spark or Apache Samza, and doing regression analysis or whatever. As Charity said before, yeah, it's hard. You need a lot of resources to generally do this, and we'll get to in a little bit, why that wasn't applicable for us. And then ad hoc metric analysis. So you go and say you have offline data, or you have data in some sort of analytics database, and after the event you say, all right, here are the metrics. Try and work out what's happening. And then alert correlation, which takes alerts from a monitoring system of things that we know are unhealthy, and then sort of puts the puzzle together of what is service A breaking service B, etc. So let's evaluate the pros and cons of each option. So real-time analytics through metrics. Real-time metric analytics through stream processing. It's usually termed anomaly detection. So the good thing is it's fast. You can do advanced insights in almost real time. The con is it's generally expensive. You need a lot of hardware to process that, depending on your setup. At LinkedIn, we have a lot of metrics, a lot. So to try and put this all into Kafka, do analysis on all of this, like we're talking millions of metrics, it doesn't scale. In some cases, there are places out there that's fine. It's not for us. Ad hoc metric analysis, smaller resource footprint. You generally don't have an SLA or a tight SLA, so you don't need as much hardware. The problem is it is slow, which in real time is, if you're trying to troubleshoot or work out what's breaking your system, that's not really ideal. And then you have alert correlation. So for us, it's actually really good because we can leverage alerts that already exist for all of our systems in our architecture, and you've got a strong signal to noise ratio. Like there's an alert saying yes, there is something broken here. The sort of problem with that is alerts are generally sort of confined to a Boolean state. They're either something's either broken or it's not, and that's sometimes not as useful as you'd like it to be. All right, so just summarizing this. So real-time analytics is expensive, but useful. Ad hoc metrics analytics is slower, but it's cheaper to implement. And alert correlation gives us a good signal. All right, so where do we go from here? So at LinkedIn, we actually had 2 smaller projects that we could sort of leverage in building this event correlation system. These were more or less side projects, but it had shown a lot of promise. So firstly was what we call Drilldown and Site Stabilizer, which is a does near-time metric analytics, which I'll talk about in a second, and it also does event correlation. So it looks at what deployments happened at in the same time period, what A/B experiments were changed, etc. And then we have Visualize, which does alert correlation. So for us, we already sort of had 2 systems that were sort of already out there that we could leverage. Excuse me for a second. So doing this, having these engines is great. But the problem is for us, we're very highly microservices dependent architecture. The ability to correlate is great, but you need to understand your dependencies. So we needed to build a call graph. And the LinkedIn stack doesn't look too dissimilar to that picture. So, in building a call graph API, thankfully at LinkedIn, our metrics are very standard. So for each dependency that my service has, I've got the same set of metrics in every application. So we can use this to map our dependencies fairly simply, actually. I was actually surprised by the simplicity of this. So what we actually have is a daemon call graph backend, and it goes and scrapes the metric list. We've got a metrics index. We get the metrics for each service, and so we basically look at 3 key dependencies. So RESTly, which is our internal API platform, so similar to Console or etcd. Voldemort, which is our read-only store, and then Espresso, our read-write key-value store. So we go there for a service. These are our main 3 dependencies in terms of like protocols. So we go and scrape the metric index, and we go and build a map of what the dependencies look like. And while we're doing this, we go and also collect the call count and the latency and the errors where applicable of what service A sees with service B, and we average this over time, and we store that data because as you'll see in a second, it's actually super useful to us. So now we have this service called Drilldown, which does near-time analytics. So using the call graph, we actually go and find what we consider to be high-value dependencies. So service A calls service B 10,000 times a second. That's high value to us. Service A calls service B 2 times a second. In all likelihood, less valuable. There are edge cases, but it fits for our use case. So we go and work out what our high value dependencies are, and we go and get the associated metrics. And what we go and do is in 5-minute chunks, we go and grab these metrics, and then we do k-means analytics on them to go and find similar trends between service metrics. And we have a queryable API where we can go and say, well, between this time and now, I'm seeing something funky on this service. Try and see if you find something that's similar on one of my dependent services. And it will give me that back. And what we get back, and I cropped the wrong part of the image, you get back a list of services and the fabric and the confidence score that we have that particular service is the problem. Then we have Visualize, which is our alert correlation system. So it polls our alerting database constantly to go and see all the active alerts on a given service. So this service knows that this alert, Visualize knows that this given alert belongs to this service. So we can say, well, oh, this service is alerting, something must be broken with it. And then we use the call graph API to sort of piece together which service is broken and then what upstreams are affected. And again, we have normalized results via an API. But we also get this really cool visualization. To walk you through it, so down the bottom we've got a really broken backend. And you can see a number of services go through the service on the left, identity, and that application looks sort of unhealthy, and its downstream looks really unhealthy. And then you can see at the top all the different front ends affected basically by this. So it is actually super useful for us to be able to visualize the problem. For our SiteOps, or formerly known as NOC team, this is super useful to sort of piece together what's going on in the larger picture. They might not necessarily understand all the dependencies. Other SREs might not understand all the dependencies between their services. So this gives a really good overview of where the site is at a given point of time. And this is actually really cool. We can actually basically create a video of what happened in an incident. So we can, using the alerts, we can say, well, we started to see one service alerting, and then we started to see more and how they interconnect. And I didn't want to risk trying to run a video during a presentation. But it's super useful to sort of visualize the what happened during an event. And it's actually super useful for postmortems as well. We can really go back and understand in a more calm situation what happened, what led up to this, when did we resolve the issue, etc. So then we have this service called Site Stabilizer. And what Site Stabilizer does is it basically takes the recommendations from Visualize and Drilldown and ranks them and basically tells us, all right, what do we really think is broken? And then we, with that, we also attach or decorate information about, why we think it's broken. So if there was a scheduled change registered in our change database during that time, we'll say, well, this might be related, or deployment events. So someone deployed the service that appears to be broken now, or if someone made an A/B experiment change during the same sort of time period. So we get that metadata, which is super useful. As Tanya said earlier this morning, like no one is at their best at 3 a.m. And when I get called at 3 a.m., any sort of information that a system can give me about what might be broken is better than nothing. So as an on-call SRE, I really appreciate that. So what does our architecture look like? So on the right, we've got our call graph system with an API. Then we've got Drilldown and Visualize, which are basically our data mining services. And then we've got Site Stabilizer, basically collating that data and decorating it for us. So the last piece is sort of accessing that data. So we have Correlate Frontend. And Correlate Frontend, its main purpose is to provide an API for our auto remediation system, which we'll talk about in a second, but also for our alert system. So if I'm 95% sure that my service isn't broken, just suppress the alert. I don't want to know about it. That does sound dangerous, so it does have to be used with a bit of caution. But I've definitely had times when I was working on other services where I wish I had this, because 99.99% of the time it was one of my two downstreams that was causing problems. So along with this API, we also provide a UI for manual introspection. So for our SiteOps team, who watch the site, they can sort of plug in the variables into this form and get recommendations, which look like this. So I've sort of mocked it up a little bit, but we basically say, hey, service C is responsible when 92% sure. And it looks like a deployment started at the same time, which correlates with this high latency we're seeing. SRE team owns the particular service, and here's the analysis from in Visualize and Drilldown, basically. So we give a lot of that metadata for our engineers to use. And when it comes to mean time to resolution, having a head start is super important. For one thing I've noticed over a period of time is trying to load, hundreds of graphs and dashboards on a slow VPN connection when I'm not at my desk is not fun, especially when stuff's on fire. So if I can sort of use one form to give me a head start on where I think the problem is, that is super useful to me as an engineer, and also to our customers who want our product fixed. So when you put it all together, now we have the same call graph on the right, and then we have our automation coming in to correlate frontend, and we also have users who will go and use our service to go and work out what's happening. So I want to walk you guys, I want to walk everyone through what this actually sort of looks like in the way that we're using it. So I'll quickly explain everything. So at the top, I have a latency alert. On the left side, I've got my alert correlation API. On the right, I've got Iris, which is LinkedIn's internal version of PagerDuty, our paging system. And then we have Nurse, which is our auto remediation system. And Nurse allows us to do complex workflows, and if something is down, we can restart it. We can go and call people. We can go and run debugging tools. We can go and log tickets. It's really flexible and really awesome. So what does our use case look like? So I have my latency alert for my front end. I want to be 85% sure that it's not my service before I go and call someone. And then I do want to call someone, so escalate to another team if we're sure. So Nurse goes and gets this alert, and it goes and calls Correlation API, and it says, what is wrong with my front-end service in data center B? So our alert correlation API via correlate frontend will go and analyze what it sees in the current state of the world, and then say, well, hey, we think service C is broken, and we're 91% sure that is what's causing it. And service C has high latency after a deploy, and the SRE owner is SRE. I didn't want to shame any SRE teams at LinkedIn. So we're sure that it's not my service, and we're pretty sure that service C is the problem, and it's owned by another SRE team. So Nurse goes and pages that team. So what this does is it enables, excuse me, it enables me, who owns my front-end service, to go and sleep, while someone else's service is on fire, and instead of me getting woken up, the team that's responsible, if they're not already awake, they will be soon. And so we can give our customers a better mean time to resolution, because we're already pretty sure we know where the problem is. I get to sleep in. But we also give that SRE, who's sort of fighting the fire now, a head start on what the issue might be. We give them as much metadata as possible. So early results. So firstly, our SiteOps, or known as our NOC team, has greater visibility on the site. If they see something strange, someone reports something strange, they can go and have a look, and they have a better understanding of how the site is behaving. Secondly, we're reducing mean time to resolution. So as soon as we see something start to go south, we can run this analysis straight away. We don't need specialists to go and, we don't need subject matter experts to go and sort of get paged, come online, spend 5 minutes trying to load graphs. We already start on where the problem is. So we can reduce mean time to resolution by, getting the right teams, right people involved very quickly. And a side effect of that is we reduce false escalations. So those people who are sort of held prisoner by dependencies, they get to sleep or they get to continue working uninterrupted, which allows us to work on other things or sleep, which both are great to have. All right, so in conclusion, so as Charity said again, event correlation is really difficult. The real-time metrics analytics stuff is super difficult unless you're a much larger company with much more resources. So sort of identifying the approach that makes sense to your infrastructure is important. Near-time analytics might be useful. Alert correlation might be useful. It's about finding what's in your budget, how your infrastructure is built, what works for you. Understanding your dependencies. So like in the microservices architecture at LinkedIn, like our velocity is so high. Like some of our applications get pushed 3 times a day. So understanding your dependencies and not assuming that your dependencies change. My colleague Ben spoke about that yesterday afternoon. Try not to make assumptions. Understanding your dependencies is important, and even the best SRE, you have the likelihood that they can remember every single dependency your service has. Good luck. So we have a machine to do it for us, and like that call graph backend system, it literally updates like every hour because things change that rapidly. Things might be added, things might be removed, SLAs might change. So understanding your dependencies is super important to being able to sort of understand the causality between service A looking broken and service B or service C being on fire. And then finally, build, integrate, and benefit. So it is great to have these correlation APIs and this front end, but the real win we get is tying it back into our automation. For us as SREs at LinkedIn, we try and have our ops work be less than 50%. So anytime, I don't need to get paged or someone bother me saying, hey, I think your service is broken, that's a win for me. So tying things into your automation, into your alerting system, you'll see wins. And to be honest, that is just as important as building the system itself. And then, hopefully once you build, integrate, everyone will benefit. People sleep, people get more work done, mean time to resolution is lower. So before I finish, I just want to give a shout out to a number of people who made this project a success. Don't know if any of them are in the room today. I can't see them. So Rusty, Reynold, who should be at the conference today, Kishore and Ranjith, who should also be here today. All those engineers put in a lot of hours to build this system, and I'm really sort of their spokesperson for today. So they've done an incredible amount of work to actually build something that is reliable and that that our whole organization can benefit from. So thank you very much. Any questions can be taken at the microphone in the middle. Thank you.
Hey, 2 questions.
Yep.
So how do you deal with fan-in? So you break your naming service and every service in that cluster is going to blame the naming service, right? So do they get 50 pages or what's the...
So our escalation system actually has a concept of like batching alerts.
Right.
So we sort of escape that.
But does that still hold true? Because you have like 5 different services, presumably they're going to be firing different alerts.
So the way we've set it up we get around that problem.
Okay, cool.
We can discuss it offline.
Yep.
But yeah.
Yeah. And the second question is, how does this tie in with, what if the dependent system that you've identified as broken is still operating within their SLA? Like, arguably, they then shouldn't be paged.
Yeah,
right?
so that's a good question. So basically, you get use cases where service A, your front end, starts to do expensive queries, and it says, "Oh, service B looks slow," but none of the other services that call service B say it's slow. It's just you. So the way that ends up working out is basically we give the results a lower confidence score, saying, "Well, we're not really sure it's this," and that sort of infers that it's probably you, not them. For things that are broken, we see higher correlation scores in the 80s, 90s. Yep.
Sorry, I think I'm asking a different question. So service B is actually slower, but they're still within their published SLA.
Yeah. So the TLDR is you'll get a lower confidence score. Yeah.
Okay, fair enough. Thank you.
Welcome.
Hey, so question about the call graph backend.
Yeah.
You said it updates regularly to
Yep.
frequently. How do you do the discovery to do that updating?
So we run Zookeeper to do service discovery using our own platform, Restly. So we sort of know which endpoints are served by which services, and then we can use the metrics from each service to work out the mappings between, all right, this service calls another service.
Okay.
It's the best way we can do it. And so we were able to sort of compute our whole call graph in about 2 minutes on a single node.
So it's like a 2 minute, does it update every 2 minutes or so?
The velocity isn't that high, so it's, I think, once every hour.
Okay.
Yeah.
Cool. Thank you.
Welcome.
Hey, does the front-end service ever find out that they did get paged, even though you slept through it because you didn't get paged? Is there any post-review, say, the next day?
No. What we're trying to do is for any, this is not pretty, but for any workflow in our auto remediation system, that my team get a tracking ticket so we can go and review the results. But no, generally speaking.
Because I have a, maybe it's not really a question, I should probably stop talking, but as a follow-up to that one, does perhaps the alert arriving at the front end is a signal that even if the back end has gotten slow, maybe you can build some extra resilience in the front end, and that you wouldn't be aware of that now that you're not sending the alerts to yourselves anymore?
So that's a good question.
It's not a question, so I'm going to sit down.
Yeah, it's actually something we're working on the side in another project, but fair point.
So my question is related to the correlation. So
Yeah.
when you have an incident, you will correlate the changes or deployment.
So
I think you based on the start time or end time.
It's more based on the start time. So we give or take a few minutes due to deployments. The actual service restarting might not line up with the deployment system starting. So we give and take a few minutes. Most of our correlation's done in real time, so there's not necessarily an end time. End time is like now because it's still ongoing.
So my question is, there might be like multiple changes in following that.
Yes.
So do you consider other features? How do you further triage?
Yes. So we actually rank what we think, we rank what we think happened at that particular time at the start time, what we think caused that. So we know that, a deployment of C service, that broke something, and we know that A and B services depend on that service. So we can rank that, we can, basically rank the events that happen at the time to give, the best result, we think.
Okay, so basically you are ranking them still based on time, but there are still some other features.
Yeah, it's difficult to say. Well, this deployment really broke something, really bad. It gets really tricky pretty quickly, and that's where you need the extra computing resources to go and then work that stuff out.
All right, thank you.
Hi.
Hey.
Can you elaborate a little bit more on Nurse? Is it a third-party tool developed in-house, and if so, how much resources?
Yeah, so Nurse is a tool that we built in-house. You'll find, if you want to talk to me later, we've got a lot of blogs and a meetup, I think, next week as well. Nurse is a workflow engine where we can give it inputs, and then we can define a workflow. And we can basically take arbitrarily, number of actions and apply rules. And we've got it to a point where it's super flexible now. So come and talk to me after. I can tell you a little bit more about it and point you to some resources that might be useful.
Great. Thanks.
Welcome.
Hello.
Hey.
So MTTR is great.
Yep.
The one thing that I'm curious about is how does MTTD come into play with all of this? Because you've said real time a couple times, and I know not everything is real time when you're detecting.
Yeah, so funnily enough, this project doesn't aim to sort of improve MTTD. Like you still need someone to notice something's broken for this to fire. In saying that,
but the two have to be connected, right? Because you're not having resolution unless you detect. Is there another system that ties into this?
I think I understand what you're saying. Yeah. So the way that we measure those, there's not necessarily a correlation, but we can talk after.
Okay. I had a second question if you're done with that. You have root cause for this? Have you ever worked in a complex system where there's only one thing that broke one thing? Because I want that job.
Fair point. So like major incidents are generally like a breakdown of a number of things, right?
Right. We work in complex
number of
systems.
processes, however you want to define that. Generally, we can link that to a particular deployment at a particular Elix, which is like the main sort of switch to the incident.
We could definitely go into that later.
Yeah.
Fair enough. Thank you.
Welcome. Just on the MTD as well, my team is actually working on a system to try and alert smarter so we catch things faster. Yeah.
Hi,
hey.
Thanks for your talk. Was wondering about the confidence score. I wanted to know, I know it's going to be relative to everyone. It's, the black art of, correlation, but do you base heavily on an alert triggering on that dependent service? Or do you guys have some funky like relative changes in latency or things?
All right,
metric-based?
so I'm going to use a screenshot. So all right, so you can see, wish I had a laser pointer. You can see on the left the identity service. It's got a number of things that depend on it. Which all sort of show a state of distress. And then the identity service heavily depends on the cloud service down the bottom. And we know that from the call graph data that we've got. And so we see that the cloud service is broken. And we also, at the same time, look at the comparison in latency or the comparison in errors to give us a higher confidence score. The other thing is, so for identity, the identity service, we've got a number of things telling us that we think that service is broken. So that also pushes up the confidence score. You can see on the more middle to the right, so feed mixer is calling cap services. So feed mixer thinks that service is broken, but nothing else thinks it's broken. So the line is not as thick. Which is basically an indicator of confidence visually. So if we did a correlation on that, in likelihood, there'd be a lower confidence score. For the drill down stuff, that's a little bit of black magic using k-means stuff. I can point you to the right people who wrote that, and they can discuss that with you further.
Great, thank you.
Welcome.
My question is fairly related. Do you have any analytics or do you do statistics on how much your correlation ID has actually saved time or something like that, or if it ever sent you to a wrong place?
Yeah, good question. We're still trying to set up some processes to do that effectively with the large number of SRE teams and other things that are going on. That it is difficult, and we launched this a bit over a month ago. So we're still sort of working some of that out. The other problem we have is we've got a number of initiatives to reduce MTTR and MTTD, so sort of working out which one of those initiatives fixed or helped that problem is actually somewhat challenging for us. But good question. Thank you. All right, thank you very much, everyone. If you've got other questions, please feel free to speak to me. Thank you.